Hi, I'm Dan Lathrop, and my group mates are Jamie Stadnick and Ben Williams, and our project is the mass optimization of a disc brake assembly. The goal of our project was to create a mass optimizer for a disc brake assembly, and the motivation was for vehicle performance as well as safety. Our design parameters included the piston area, the rotor effective diameter, rotor thickness, and an assumption that was made is that the material for the rotor is gray cast iron and the caliper material is cast aluminum. We ran a regression to relate the system mass to piston area, and we came up with an equation to model mass versus weight. This equation can be seen on the lower right hand portion of the graph. Challenges that we ran into when modeling this was a discrete jump that was determined by the number of pistons, and we used a ceiling function with the largest piston size from the data collected to model these discrete jumps.
So our first constraint placed on the system is a sizing constraint to determine whether or not the driver can actually exert enough brake force on the corners when in an emergency situation. So for this we use the coefficient of pressure, which is just a constant relating the input pressure to output brake torque. So for this, a subfunction called CP solver was used in order to find the minimum possible coefficient of pressure for the front wheels to ensure locking. Some key assumptions for this were that we just assumed constant coefficient of friction for the tires and pads, despite there being nonlinear effects in both systems in reality, and also assuming no aerodynamics. So for our thermal constraint, this was based on what the max heat rejection of the system would be at its failure temperature, which was determined to be the boiling of the brake fluid. And we wanted to see whether or not this max heat rejection would match the max heat flow into the system under its worst case scenario, which would be a max G braking scenario. For this, the primary assumptions were that the caliper and rotor were treated as a lump body with the same temperature, gray body radiation of both systems, and that the geometry of the caliper was assumed to be a capsule to relate its volume to its surface area. For the structural constraint, this was basically a rudimentary surrogate modeling from one run of finite element analysis to determine what an acceptable stress state would be for one instance of a rotor placed under a moment, and then from this extrapolating based off the percentage increase in both the moment and the moment arm, what the required increase in the rotor thickness would be. So finally, our bounds were for the rotor effective diameter based off of, on the lower bound, the standard lug pattern for a very small OEM automotive wheel, and on the upper bound based off of the user inputted wheel radius with some additional clearance. For the piston area, it's based off of the max and min from the data that we collected. And then for the rotor thickness, the upper bound is based off of what is feasibly accommodated by most caliper packaging, and the lower bound is mostly arbitrary since that is in reality in the simulation set by the structural requirement.
Here is our system model. And for our model analysis, we did sweeps of vehicle parameters for the optimizer to see which vehicle types are valid. And we found that our optimizer was valid for high-performance vehicles with longer wheelbases and lower centers of gravity. Here are our optimization studies and results. For FMINCON, lambda was positive for the lower bound, upper bound, and thermal constraint, indicating that these were active constraints, and lambda was negative for the brake force constraint, indicating that it's a redundant constraint. Our genetic algorithm implementation found a less optimal solution, and pattern search did not find a feasible point, so pattern search is insufficient for our optimization problem. And in conclusion, some assumptions were made while calculating brake sizes, and they were the primary source of error. But these assumptions were made in order to reduce the scope of the project, and the goal of the project was just to create a general optimizer for designers.